Hello, I'll be presenting on, as you said, reconstruction of smoothly joining 3D printed restorations to fix broken or damaged objects. So to begin, let's look at the life cycle of common household objects. Most objects are purchased and then used for a period of time until finally at some point in the future they're broken. At this point, most consumers would choose to simply discard the object, but there's another more preferable option, and that is to attempt to repair and then reuse the object. This is both more economically sustainable because the user doesn't have to go out and purchase a replacement object for this broken object, but it's also more environmentally sustainable because the user doesn't end up throwing out this object and contributing additional trash by doing so. However, it's much more difficult. The user has to manually reassemble all of the fragmented parts, and if any of the parts have been destroyed or lost during the breaking process, then repairing the object in this way may simply not be possible. We present a system by which users can automatically generate 3D printable restoration parts in order to fix their broken objects. This completely circumvents the problem of having to manually reassemble the object or the fragmented parts, and is still able to generate restorations even if the fragmented parts have been destroyed or lost. As input, our approach takes a 3D scan of the broken object and a 3D scan of a corresponding original unbroken object. The requirement of the original object isn't unreasonable because a lot of the objects that we break most frequently come in sets or pairs. For instance, a pair of bookends or a set of china plates. Once the two scans have been collected, a naive approach to generate the restoration part would be to first align the two objects and then compute the Boolean subtraction of the broken object from the unbroken object. However, because of very small imprecisions in 3D scanning sensors, doing this generates a restoration part with surface artifacts and mesh slivers on the surface of the broken object, and thus generates a restoration part that's functionally unusable. An approach to circumvent this, which gets around the problem of artifacts, is Euclidean distance thresholding, wherein once the two objects are aligned, for each vertex in each object, the distance to the nearest vertex in the opposing object is computed, and if this distance is less than a threshold, then the vertex is discarded. The mesh parts can then be triangulated to generate the restoration part. However, this approach generates restoration parts with very obvious striations as well as a deep rut or furrow at the join between the two objects, and as a result, these objects are also functionally unusable. In contrast, our approach generates a restoration part with a smooth, continuous, not mathematically continuous, but visually continuous join between the restoration part and the broken object, making it an ideal candidate for object repair. A couple of other approaches exist to generate these restoration parts, but they usually fall into one of two categories. The first of which is a manual approach, which requires the user to manually generate the restoration part, usually using either a 3D scan or other information about the broken object as a guide in the process, sometimes like a sketch. This has been shown effective to generate restoration parts for human ears and also for a couple of cultural heritage objects. But this process is very involved. It usually requires cropping of the broken object and then eroding it using some mesh tools, and it's really kind of unreasonable to expect the average consumer to be able to generate a restoration part that mimics the complex geometry of the fractured region of these broken objects. The other approach is more automated and requires first extracting a plane of symmetry from a broken object and then reflecting an unbroken portion of the object onto a broken portion and computing the Boolean subtraction, and then usually following this up with some manual mesh refinement steps. This has been shown effective to generate restoration parts for human skulls and again for some cultural heritage objects. But if the restoration part doesn't, or I'm sorry, if the broken object doesn't exhibit a plane of symmetry or is symmetrically damaged, then this approach just fails to generate a restoration part. For our approach, once the user has collected the two input scans, we align the two input scans using a combination of Super4 PCS and ICP algorithm. We extract a region of the original object which corresponds to its contribution to the restoration part, which we term the exterior mesh. We then extract a region of the broken object which corresponds to its contribution of the restoration mesh, which we term the fracture mesh. By combining these two meshes and triangulating the gap between them, we can generate the final restoration mesh, which can then be 3D printed to generate the restoration part. Besides the input of the 3D scans, the only input that our approach requires is the number of resulting connected components. In this case, it's just one because the user just wants the head of the duck as an output. To generate the exterior mesh, we first select the vertex in the original mesh that is farthest distanced from any vertex in the broken mesh and iteratively add vertices to this mesh as long as they are at least a threshold mu from any vertex in the broken mesh. This effectively extracts regions of the original mesh that are distanced from the surface of the broken mesh while still retaining as much of the broken mesh as possible. However, this doesn't prevent mesh intersections, as shown on the left-hand side here, which are undesirable. So before generating the exterior mesh, we first compute a value eta corresponding to the minimum edge length that any edge in either mesh must have in order for intersections to possibly occur. To prevent them from occurring, we then upsample faces on either mesh that have any edge length that's greater than this value eta. And this prevents the possibility of intersection by ensuring that both meshes are sufficiently dense. Now that we've extracted the exterior mesh, we can go about extracting the fracture mesh. To do this, for each vertex V on the exterior mesh boundary, we select a vertex V bar that minimizes a optimization function that's composed of 3 terms. The first term ensures that the vertex selected in the broken mesh is nearby the vertex in the exterior mesh. And if we were to just minimize this term, we'd get a restoration or a join between the 2 objects that looks like this. As you can see, though it does join the 2 objects, there's a very obvious furrow or rut between the 2 objects. So to refine this join, we add a second term. And this term requires that the normals of the 2 vertices selected are close to each other or are roughly similarly oriented. This does improve the restoration join a little bit, but as you can see, there's still a pretty obvious rut or furrow between the 2 parts. So to further refine this, we add a third term, and this requires that a vector drawn from the vertex in the exterior mesh to the vertex in the broken mesh is roughly tangent to the relative surface of the vertex selected in the broken mesh. And this finally generates what we're looking for, which is a nice smooth join between the 2 parts. At this point, we've selected a sequence of vertices on the broken mesh, but in order to identify specifically the fracture mesh, we need to resolve these into a cycle. To do this, we connect successive vertex pairs on the broken mesh using Dijkstra's algorithm. But this resulting cycle can contain vertex repetitions like this one, which will generate self-intersections later on. So to eliminate these, we iterate over the vertices of the projected cycle like this. And then if we ever encounter a vertex repetition, we remove all the vertices between the current occurrence and the first occurrence of the vertex, removing the whole section that's been repeated, and then remap the correspondence to point to the current vertex, and then continue iterating until there are no vertex repetitions remaining. At this point, we extracted a simple cycle on the surface of the broken object. To identify the fracture surface, or the fracture mesh, we extract faces on the surface of the broken object whose orientation corresponds with the orientation of the projected cycle. These faces will reliably lie underneath the exterior mesh and thus belong to the fractured surface. To identify the fractured surface from these, we just take the intersection of these faces that we've computed with the connected components that result by removing the projected cycle. And by doing this, we get the middle red mesh there. Now that we've extracted the fracture mesh, we can safely discard the remainder of the vertices in the broken object. And at this point, we just have the exterior mesh and the fracture mesh. To generate the final restoration mesh, we recompute our previously computed correspondences by, for each vertex in the exterior mesh boundary, computing the closest vertex in the fracture mesh boundary, and then using these correspondences to triangulate between the 2 meshes. This generates the final restoration mesh, which can then be 3D printed to generate the restoration part. Here are a couple of our results. As you can see, the restoration part fully restores the object's dimensions, and in some cases, like the center case with the white dog, you can even stand the broken object up on its restoration part. We generate results for a variety of objects, both functional and non-functional. Some objects, like the candle stand and candle holder on the top left, can again be used for their desired tasks, and the owl cup can again be used to drink from comfortably without any fear of cutting yourself from rough intersections between the restoration part and the broken object. More ornamental objects, like the Winnie the Pooh figurine and the Mario figurine, though they were unrecognizable when they were broken, can again be recognized due to our restoration part. To demonstrate the effectiveness of our approach, we compare our approach to that of 4 other approaches and then variations on our approach. The first approach we compare to is Boolean subtraction, which generates artifacts and mesh slivers on the surface between the broken object and the restoration part, making it unusable for the purposes of repair. The second approach we compare to is that of what we're going to term altered Boolean subtraction, wherein the two objects are again aligned, but in this case, for each vertex in the original object, the distance to the closest vertex in the broken object is computed. And if this distance is less than the threshold, then the vertex in the original object is moved to the position of the vertex in the broken object. This eliminates a lot of the artifacts that are present in Boolean subtraction, but as you can see, it doesn't eliminate all of them. And because it's still a Euclidean distance operation, there's still a furrow at the intersection between the broken object and the restoration part. We also compare our approach to that of naive Euclidean distance thresholding, which demonstrates similar problems with the striations between the intersection as well as the same furrow. And finally, we compare our approach to the approach of Papiano et al., who have the most well thought out automated approach prior to ours. In this approach, a plane of symmetry is first computed for the object, and then an unbroken portion of the object is reflected onto a broken portion, and the Boolean subtraction computed. They use this to generate the fracture mesh, and then to generate the exterior mesh for each vertex in the original object, they compute the distance to the closest vertex in the broken object and discard it if it's below a threshold, similar to the process of the naive distance thresholding. But because this process is still Euclidean-based, or Euclidean distance-based, it still suffers from the drawbacks of the furrow at the intersection. And because very few of our objects exhibited symmetries, this approach failed to generate restoration parts for most of our objects. Finally, we generate results for 3 variations on our approach: one that minimizes the first term of our objective function, one that minimizes the first 2 terms, and finally our final approach, which minimizes all 3 terms. To generate quantitative results for each approach, we first remove vertices in the approach that were contributed either by the original object or by the broken object, which results in only faces that were generated by that particular approach, so only faces at the join between the 2 objects. We then upsample these faces and then compute the average distance from vertices in these faces to either the original object or the broken object. Here's a comparison of all of the approaches. On the vertical axis, we show the average distance, and in this case, lower is better because it indicates that the restoration part very closely mimicked the geometry of either the original object or the broken object. We show results for naive Boolean and altered Boolean in blue, naive thresholding, and the approach of Papiano et al. In orange, and finally variations of our approach in grayscale, with our final approach being shown in white. Our approach performs better than all other approaches for all these tasks, except for the approach of Boolean subtraction, which generates very little additional geometry and as a result performs very well here. But because it generates many surface artifacts and mesh slivers, it's still unusable for the purposes of repair. A couple of limitations of our approach are, in order to extract a fractured surface, we assume that the interior of all broken objects is solid. Though this works for most objects, some objects, like salt shakers, have their functionality tied to their interior structure. And as a result, though our process restores these objects' dimensions, they don't restore the object's functionality. Our approach is also unable to generate or unable to connect a single exterior mesh boundary to multiple broken objects because this would require triangulating between multiple independent objects. This can sometimes occur when an original object has multiple appendages, all of which are broken off, and the user attempts to reconstruct a restoration part from the appendages that are broken off. However, this can be resolved by rerunning the algorithm with a lower value of mu, allowing the exterior mesh to creep closer to the broken object and resolve itself into the appropriate number of boundaries. Finally, the restoration parts that we generate are a very obviously different color than the original object. And though this is preferable in some circumstances, like the restoration of cultural heritage objects, where correct attribution requires that the restoration part be a different color than the original object, most users would probably prefer their restoration parts to restore the object's color as well as its size. In the future, we'd like to be able to generate repairs that take into account limitations of 3D printing. Because of their complexity, a lot of our restoration parts need to be printed with 3D supports, and if the supports are printed on sensitive object regions like the fractured surface, the restoration part may no longer fit to the broken object correctly. In addition, some 3D printers very slightly expand the objects that they print, and as a result, if the restoration part fit very closely to the broken object, then the 3D printed part may not fit at all. To combat this, in the future, we hope to export additional information to the user during the reconstruction process about how to best orient their object during 3D printing to avoid printing on sensitive regions like is shown on the left-hand side. And we also hope to export dynamically sizable restoration parts that the object or that the user can select in order to compensate for any expansion during 3D printing. Finally, in the future, we'd like to be able to generate restoration parts even in the absence of the original object or the original mesh. It's sometimes the case, like for antiques and for maybe personal mementos, that a corresponding original object may simply not exist. So in these cases, we'd like to use an approach similar to that of Sorkane et al. To automatically deform an input model from an online repository to fit the broken object and then be used as an input for our system. Though we've tried this approach, or an approach similar to this, using a ordinary-looking mug to generate a restoration part for a kind of owl-looking mug from an online repository, our implementation only included proximity constraints. And as a result, the restoration process required a couple of manual steps. And as you can see on the far right, the restoration part doesn't fully fit to the broken object. There's a little bit of a white fractured surface over there. So in the future, we'd like to create a deformation approach that takes into account, or that includes the conditions of tangency as well as normal alignment into the deformation process. We've also looked at a couple of approaches to automatically generate the original object. Most interestingly, a generative adversarial network and an approach by Rock et al. To automatically create complete 3D meshes from incomplete depth scans. The more promising of these is the one by Rock et al., but if we were to directly feed the output of their approach as the input to our approach, the restoration parts that it would generate would be malformed and show non-smooth joins. So we'd have to retrain their approach or tweak it quite a bit. However, if we were able to adapt approaches similar to that of Rock et al. And Sorkane et al. To first automatically generate the original object and then automatically deform it to the broken object, we could automate most of our input pipeline for the original object. This would effectively allow anyone to automatically generate a restoration part for their broken object with only a 3D scan of the broken object as input. And this is where we think the future of 3D printable restorations lie. Thank you very much.